Hey everyone, so today we're going to tackle joint probability. And if that sounds a little intimidating, don't worry. I want you to forget the formulas for just a minute and think of it more like a visual puzzle. Because the real secret here, it isn't about super complex math. It's about learning how to draw the right map. Let's dive in.
All right, to kick things off, let's start with a classic problem. Seems simple enough, right? But you've got two completely random things happening at once, when Alice shows up and when Bob shows up. How do you even begin to combine those two things to get a single answer?
You see, with just one random event, you can kind of picture all the possibilities on a simple number line. But when you've got two, like Alice's arrival time and Bob's arrival time, a line just doesn't cut it anymore. We need a plane. Think of it like a map, where every single point, every coordinate, represents one possible way their meeting could play out.
And that right there leads us to the golden rule, the single most important rule for everything we're about to cover. And I mean it. Before you even think about an equation, before you write down a single integral, you have to draw a picture. This picture is your map of every single thing that can possibly happen. And look, this is a quote straight from the source material this is all based on, and it is the absolute key. This step isn't just a helpful hint, it is fundamental. So what exactly is this support set we're supposed to be drawing?
Well, think of it this way. The support set is the boundary of your map. It's the playing field. It's the shape that contains every single valid outcome. If a point is inside the shape, it can happen. If it's outside, nope, impossible, it's out of bounds.
So for a problem like the one with Alice and Bob, our map might look something like this gray rectangle. We could say the horizontal x-axis is Alice's arrival time, and the vertical y-axis is Bob's. Any point inside this shape is a valid possible outcome. Any point outside can't happen. This map, this becomes our ground truth.
So, let's start with a simple case, where our map of possibilities is just a nice, predictable rectangle.
Okay, here's the joint probability function. Now don't get hung up on the formula itself. Seriously, ignore it for a second. The really important part, the part that tells us the story, are those conditions. They're telling us x can be anything from 0 to 1, and y can be anything from 0 to 2. That's what draws the borders of our map.
So on one side you have our map, that rectangle we just defined. That's the entire world of possibilities. Then we ask a specific question like, what's the probability that x plus y is greater than or equal to 1? Well, that question carves out a specific piece of territory on our map, that blue area. To find the actual probability, we basically need to measure how much probability stuff is packed into that blue region. And for that, we need to pull out a tool from calculus.
And this is the magic moment. The map we drew becomes a direct guide for the math. To measure all that probability inside the blue shape, we use a tool called a double integral. Just think of it as a fancy way to add up all the tiny bits of probability within a shape. And the key is that the edges of our blue shape, the lines of the rectangle and that diagonal cut, they tell us the exact start and end points for our calculation. The drawing literally tells the math what to do.
Okay, so rectangles are pretty straightforward. But what happens when our map of possibilities isn't so simple? Let's move on to a case where the shape itself introduces a really fascinating twist.
All right, let's look at a new function. Now, the first couple of conditions seem familiar, right? But look at that third one. X plus y must be less than or equal to 1. Believe me, that one little constraint is a total game changer. It's going to completely warp the shape of our map.
And bam, look what that new rule does. Our map of possibilities is no longer a simple rectangle. It's a triangle. And this is a huge deal. Why? Because now the possible values for y depend on the value of x. Think about it. If x is way over at point 8, y has to be really small to stay inside the triangle, right? But if x is just point 1, y has a whole lot more room to roam. That relationship, that dependence, it's baked right into the shape of the map.
And of course, this new shape directly changes our math. When we're setting up our integral, the upper limit for y isn't a fixed number anymore. It's now that diagonal line, the function 1 minus x. The ceiling of our map is sloped. This is something you would have absolutely no way of figuring out without having drawn the picture first. No way.
So this whole idea of one variable putting limits on another one, that leads us to a really crucial concept in statistics, independence. And it turns out our visual map gives us a super powerful and intuitive way to check for it. Let's just put our two maps side by side.
On the left, with the triangle, if I tell you x's value, you immediately know more about y's possible range. They're connected, they are dependent. But on the right, with the square, if I tell you x's value, it tells you absolutely nothing new about y. Y can still be anything from 0 to 1. They're totally free of each other. They are independent. The shape tells the whole story.
So we can boil all of this down to a simple visual checklist. For two variables to be independent, two things have to be true. First, their map. The support set must be a rectangle. No triangles, no weird shapes. A rectangle. Second, the probability function itself has to be separable, which just means you can split it into a piece that only has x's in it, multiplied by a piece that only has y's in it. If you can do both those things, they're independent. All right, we've covered a lot of ground here, from rectangles to triangles to independence, but if you remember only one single thing from this entire explainer, I really want it to be this.
This quote from the source material just says it all. Drawing the map isn't a helpful hint. It's not a suggestion. It is a necessity. Without that visual, you are flying completely blind. You simply cannot set up the problem correctly.
And this really is the whole process. It's a simple, repeatable framework. First, you draw your map of all possibilities. Second, on that map, you shade in the specific outcome you're interested in. And third, you let the boundaries of that shaded region tell you exactly how to set up the math.
So let's circle all the way back to that first question. What were the odds Bob has to wait for Alice? Well, waiting just means Bob arrives before her. So we draw our map. Alice's arrival, the x-axis, goes from 0 to 1 hour. Bob's arrival, the y-axis, goes from 0 to 2 hours. The total area of all possibilities is a big rectangle with an area of 2. Now the little slice of that map where Bob arrives before Alice forms a triangle with an area of 1/2. So the probability is just the area we want, 1/2, divided by the total possible area, 2, which gives us our answer 1/4 or 25%. We solved it not with some crazy formula, but just by drawing a simple shape.
This visual method, this mapping of possibilities, is incredibly powerful for two variables. Which, it naturally leads to the next question. What would the map look like for three variables? It wouldn't be a flat shape anymore, would it? It'd be a solid object. And what kind of problems could we solve then?